Hi everyone, welcome to our video lecture for section 10.5 on the comparison tests. In our previous lecture, we went on to learn 3 more tests for convergence or divergence. We learned about the divergent test, or the nth term test for divergence, and for this test, we looked at the limit on the nth term as the n went on to infinity. If that limit was not 0, then we knew that the series diverged. However, if the limit was 0, then the test was inconclusive, so we went on. Next, we learned the integral test, and for this test, we learned to compare the series to a corresponding improper integral. If the integral converged, so did the series, and if the integral diverged, then so did the series. Then, we used the integral test to develop the p-series test. If our series was of the form 1 over n to the p, then we can tell immediately whether the series was converging or diverging simply by taking a look at the value for p. Now, in this video, we're going to be taking a look at 2 more tests, the direct comparison test and the limit comparison test. So let's go ahead and begin here with the direct comparison test. Let a be less than a sub n, which is less than or equals to b sub n for all n. Now, before we move any further, I want to clarify what this inequality is telling us. Notice that a sub n and b sub n are all greater than 0, so that means that they're all positive terms. So this means that this direct comparison test will not work for sequences that have negative terms. Alright, so with that out of the way, let's take a look at what the direct comparison test says. If the infinite series for v sub n converges, then the infinite series for a sub n also converges. And if the infinite series for a sub n diverges, then the infinite series for b sub n also diverges. So in other words, what this is telling us is, if all of the terms on a given series are less than the corresponding terms of a convergent series, then the given series converges. On the other hand, if all of the terms are greater than the corresponding terms of a divergent series, then the given series also diverges. Now, before we take a look at a couple of examples, I want to give you guys a couple of hints and pointers. So we need to know what series to compare to, and you need to be able to easily show the terms for one series are greater or less than the terms for the other. And the test can in some cases be inconclusive, so in that scenario, we would need to use other tests. Now, when handling the comparisons, I would consider comparing to a geometric series or a p-series. Those are normally the easiest scenarios. Now, to select what to compare to, you can think of the n behavior for a series. So for example, considering the following, there's functions here, but let's go ahead and consider the following series. So first, we have the infinite series of n squared plus 3n minus 5 all over n to the 5th minus 4n cubed plus 7n minus 5. Alright, so if we wanted to figure out if this infinite series was converging or diverging, we needed to compare to some other series. But what's a good idea? And this is what I mean by taking a look at the n behavior. So if you consider this one here, and you can think of it as a function, if we had like n squared plus 3n minus 5 all over n to the 5th minus 4n cubed plus 7n minus 5, thinking about the n behavior, you know that only the terms with the highest powers are the ones that are going to come into play. So on the numerator, I can ignore the 3n minus 5, and on the denominator, I can ignore everything and just focus on the term with the highest power, the highest degree. So this one here is the n to the 5th. Now we can simplify this even further, canceling out an n squared on the numerator, leaving us only with an n cubed on the denominator. So a great series to compare this original series will be the p-series, given here by the sum as n goes from 1 to infinity for 1 over n cubed. Now this one here has a p-value of 3, so we know that this p-series converges. Now what about the other series here, given here by the sum as n goes from 1 to infinity for 3 to the n divided by 7 to the n plus 9n minus 3. So taking a look at this one here, and again, analyzing the n behavior, it looks like on the denominator, the term that's going to be overtaking the other ones is the exponential. So the 9n minus 3 don't even count. So an excellent series to compare this one to would be the series 3 to the n over 7 to the n, which could be rewritten here as the sum as n goes from 1 to infinity for 3/7 raised to the n. Now this one here, you can easily recognize that this one is a geometric series with an R value of 3/7, which is less than 1. So this one here is a converging geometric series. And this is going to be the crux for this particular section. We need to take a look at a series and identify another series that it would be good to compare to. Now, knowing where our comparison series converges or diverges will help us understand if the original series will converge or diverge as well once we take a look here at the properties, or once we compare which one is bigger or smaller depending on the problem. So, to make this a little bit more clear, let's go ahead and take a look at a couple of examples. Now, as you're working with these problems, I do want you guys to let me know what series you're comparing the original one to, and whether or not the one that you're choosing to compare is going to be diverging or converging. So, let's begin here. So for our first series, we have the sum as n goes from 1 to infinity for 1 over n squared plus 2. All right, so will this one here be easier to compare to a geometric series or a p-series? Well, since I'm dividing here by an n squared, then I think a good series to compare it to will be the series 1 over n squared. Now this one here, is it diverging or converging? Well, this one here, it's a p-series with a p-value of 2, so this one converges. Why? Well, because it's a p-series with a p-value of 2. Okay, so this is very similar to what we did before, but now let's actually go ahead and use the comparison test. So in order to do that here, I want you to think about which is bigger, the 1 over n squared plus 2 or the 1 over n squared. So which one is greater? Now again, remember, the larger your denominator, the smaller the quotient. So in this case, the 1 over n squared has a larger denominator, so that means that the quotient or the fraction 1 over n squared is larger. And this is always what I want you to do. Once you figure out your series to compare to, take a look at the general terms and ask yourself, which one is greater? Because why do we want to do that? Well, we know that 1 over n squared is greater, and we happen to know that this one here converges. So if the largest one converges, then we know that the smallest one, or the smaller one, will also be converging. So for our answer here, we can just say, therefore, the series as n goes from 1 to infinity for 1 over n squared plus 2 converges. Now it converges by the direct comparison test, which I'm just going to go ahead and abbreviate as DTC. There we go. Okay, so now let's take a look at another example. So now we have the series here as n goes from 1 to infinity for 1 over 3 plus 2 to the n. Which one is a good series to compare this one to? Well, you probably guessed it. This one here could be very easily be compared to the series as n goes from 1 to infinity for 1 over 2 to the n. Now, as I'm writing this one here, 1 over 2 to the n, you can also think about this one here as being essentially a geometric series of 1/2 raised to the n. Now, this one here has an r value of 1/2. I'll put here r equals to 1/2. So this one here is going to be converging because it is a geometric series with an r value of 1/2. Okay, so we know this one is converging. So let's take a look here and compare our two formulas, or our two general terms. We have 1 over 3 plus 2 to the n, and we have 1 over 2 to the n. Okay, now which of these ones is bigger? Now, very similar to the one that we just did, the bigger the denominator, the smaller the quotient. So for this one here, 1 over 3 plus 2 to the n is larger, so therefore that fraction is going to be smallest, or smaller. So the larger of the two is the one that we chose to compare. Now, we already know that this one here was converging. So if the largest one converges, then the smaller one also converges. And I guess I'll do that here for the one above as well. Okay, so with this comparison, we get to see here, therefore, the series as n goes from 1 to infinity for 1 over plus 3 to the 2n converges by the direct comparison test. Perfect. Okay, so now let's take a look at another one here. So for this next one, we have the sum as n goes from 1 to infinity for 1 over the square root of n minus 4. Now this one here, we can compare it to the sum as n goes from 1 to infinity for 1 over n to the 1/2. Now once more, we are dealing with a p-series, and this one here, p is equals to 1/2, which is less than 1, which means that it will diverge. Why? Well, again, because it is a p-series with a p-value of 1/2. So this one is converging. So now let's go ahead and do the comparison. If we compare 1 over the square root of n minus 4 to 1 over the square root of n, which one is greater? Now for this one here, it might not be as easy as the other ones. So if you're having trouble, you can always just pick some n value. I'm going to say that n, let's say that n is equals to, I don't know, 25. If n is equals to 25, then I would have here 1 over the square root of 25, which is 5, minus 4 is 1. And on the other formula, we're going to have 1 over the square root of 25, which is 5. All right, so which one is bigger? Okay, so now we get to see here that 1 is bigger. Okay, so what is this telling us right now? Well, we don't know whether the original series is going to be converging or diverging. We know that this one is diverging. So what does the direct comparison test tells us? Well, going back to it again, if the larger of the series converged, then the smaller one also converged. However, if the smaller one of the series diverged, and it's the smallest one because we know that a sub n is less than or equals to b sub n, then if the smaller one is diverging, then the larger one is also diverging. So, because the smaller one is diverging, then this one here also diverges. Okay, so with this information, we can say, therefore, the series as n goes from 1 to infinity for 1 over the square root of n minus 4 diverges by the direct comparison test. Okay, now let's take a look at one more here. Now this one here is very similar to the one that we just tried, but it's a little bit different because, well, in the denominator, now you're adding 4. So, if we choose a series to compare it to, I'll put here compare to, and just as we did above, I'm going to go ahead and compare it to the series 1 over n to the 1/2. Now we know that this one here was diverging, so I'll put here which diverges because it is a p-series that has a p-value of 1/2. Okay, now which one is bigger? Is the 1 over the square root of n plus 4 bigger than 1 over the square root of n? And again, if we repeat the same value of 25 for n, so just to compare it here, we would see here that now we would get a 1 over 5 plus 4, so we would get a 1/9 and a 1/5. Now which one is greater? Well, now the 1/5 is greater, so we are in a little bit of trouble here, because now we know that the larger is diverging, but the direct comparison test doesn't really help us here. It helps us if the smaller one is diverging, but if the larger one is diverging, yeah, we have no idea what's happening with the smaller one. Could be diverging, could be converging, who knows? So for this scenario, the test is inconclusive. Okay, so hopefully with this couple of examples, the direct comparison test is making a little bit of sense, or hopefully a lot of sense. And again, remember, if you can, you always want to compare a given series to either a p-series or a geometric series. Okay, so this is where we are going to be stopping for our part 1. we'll continue on with part 2, talking about the limit comparison test. I'll see you guys in part 2.